So, welcome to this advanced manufacturing and process modeling course. Today we are meeting to discuss a new module, that is advanced additive manufacturing and process modeling. So, we will discuss about the fundamentals associated with additive manufacturing briefly, and also we will see how we can apply process modeling tools such as computational fluid dynamics based process modeling to understand the thermosolutal convection, fluid flow, heat and mass transfer situations prevails during rapid solidification happens in case of additive manufacturing. We will learn about both laser based and arc based additive manufacturing processes, and also we will discuss about how we can develop near accurate phase field models to simulate the microstructure evolution in case of additive manufacturing. So that we can have a idea about the quality characteristic beforehand, and we can gain insight into the physics of the process thereby, and also we can optimize the process variables. There are several process variables in additive manufacturing. We will learn about that while discussing this module. So, so that is basically the essence of the numerical modeling, to grab insight into the physics and also to optimize the process conditions. So, with that let us start with the today's lecture. So then what is additive manufacturing? So, additive manufacturing is a process of joining materials to make parts from 3D CAD model data layer upon layer, as opposed to subtractive or formative manufacturing methods. So, for example, if I draw a typical cube over here. You can see that so then if I need to develop this cube by additive manufacturing, then there has to be slices made, and then we have to develop this cube in layer by layer fashion like this. Okay. So, so then this is this is the first slice, and then this is the second slice. So, likewise you can so based on the CAD model present you can develop the entire structure. So, this is about this is called additive manufacturing. So, it is detailed in ISO and ISTM 52900 20215 standards. The core principle, so AM involves joining materials using energy sources to create micro to macro scale dimensions, build layers sequentially resulting in 3-dimensional objects. And materials and energy sources. So, material types, almost all the materials like metals, polymers, ceramics and composites can be processed using additive manufacturing tools. Now, in this case composites can be either CMC, that is ceramic matrix composites, or MMC, metal matrix composite, and even polymer matrix composite PMC are. So, all the classes of composites are possible to be processed, and the parts can be developed from them adopting additive manufacturing techniques. And material forms include powders, wires, rods and sheets. Okay. So, so we will learn that so these powders can be processed by laser, and also wires also can be processed by laser, also can be processed by arc. So, there are different energy sources, there are also different materials that are possible, different material forms like in powder, wire or rods and even sheets which can be joined sequentially, or which can be cured in layer by layer fashion to get the 3D part made. And different forms of the material, there are different energy sources like laser beam, electron beam, ultrasound, friction, as well as other forms of energy sources can be employed to perform the additive manufacturing and develop the parts out of it. So, energy transforms the feedstock into a consolidated solid layer, and then the adjoining consolidated solid layers forms the 3D object. Okay. So, so the components of AM, type of energy source, as I already told, like laser, electron beam, arc, etc. Physical phenomenon is fusion, solidification. Material type also, like I discussed, metal, ceramic, polymer and composite. And so, the energy feedstock interaction is heat and mechanical bonding. And then processing parameters, energy source, speed, feedstock deposition, material flow, etc. There are several other processing parameters that we will discuss subsequently. And so, the material efficiency, the key advantages of additive manufacturing is the number one is material efficiency. So, AM processes are highly material efficient, minimizing waste compared to subtractive methods used in conventional manufacturing. So, for example, if you can recall that we have discussed about casting, we have discussed about metal forming. So, all these manufacturing techniques. So, after developing the initial preforms, we need to machine those preforms, so that we can arrive at the desired component geometry. Just a minute. Okay. So, desired component geometry. So, the preforms need to be machined, so that we can arrive at the desired part geometry. So, then in the machining process, there are several material wastage that happens. So, all these material wastage can be nullified in case of additive manufacturing, because additive manufacturing is a net shape manufacturing process in true shape, okay, true sense, okay, net shape manufacturing process. So, where we can it is possible to develop parts without any post processing involved, like machining or grinding, etc. Okay. So, that is a advantage of AM in terms of material efficiency. And then the next in the line is the ability to produce complex parts. So, additive manufacturing enables the fabrication of complex geometries that are difficult or impossible to achieve using traditional manufacturing techniques. So, for example, like we have discussed in detail in case of casting. So, if we need to make any assembly, so we need to or a typical part, we need to first make the mold. Mold can be made of sand or can be made of metal, but first step, like in case of casting also, in case of powder metallurgy also, we have to make a mold, and then that mold has to be utilized to develop the part. In case of casting directly, the cast parts is developed by solidification of the liquid melt, and in case of powder metallurgy, it is the green compact, the powder preform, and then that need to be cured or sintered to arrive at the final part. So, out the component. Whereas in case of assembly, like if I draw a simple part. So, say if it is a so if it is a combination of there are say 3 or 4 parts. So, you can see that there are complicated geometries involved, and so then in some way by machining or otherwise after casting or maybe after forging. So, these parts need to be assembled or joined to get the entire assembly made, whereas the same assembly can be manufactured in adopting AM route as a single part. So, that is a big time and cost based advantage. So, so what you can so as we already learned that additive manufacturing can save the material in a in a great extent, by minimizing the wastage, and also it can save a lot of time, and like it by towards development of the complex geometry parts, and also it can develop multiple parts at as a in the form of a assembly into a single part at one go. So, that is the advantage. So, that is also about the next topic, that is streamlined assembly. So, combines manufacturing and assembly into a single step, reducing the need for multiple assembly stages. So, this is what I have discussed. So, going ahead, the customization and flexibility. So, allows for the creation of personalized and highly customizable parts, enables the production of unique tailored designs through digital interfaces. So, so then AM, another key advantage of AM is to provide immense design freedom. So, you can see that there are several different complicated design parts are possible to be manufactured by additive manufacturing, which are otherwise very difficult to manufacture by other conventional routes like casting or forging. So, because of there are difficulty in terms of ensuring flowability of the material, fusion between different layers, and also difficulty in manufacturing appropriate mold or die to get the shape made, whereas in AM, because it is a preform manufacturing, there is no need for any dies. So, that is why the material can be either it can be in the form of powder form or in the form of wire form. So, they can be directly melt or even also can be sintered, and then the required shape of the object can be made. For example, the like lattice structures. So, lattice structures can be made very quite easily in 3 dimensions using additive manufacturing, which is otherwise very difficult to make by conventional manufacturing techniques. And number 5 is thermokinetics flexibility. So, AM offers control over thermal and kinetic processes, so which are limited in conventional techniques, allows for optimization of mechanical properties during fabrication. So, these are the key advantages associated with additive manufacturing. So, now let us discuss about the classification. So, additive manufacturing can be broadly classified into 3 categories. Number 1 is solid based. Solid based, it is the subcategories or different techniques under solid based AM are laminated object manufacturing, loam, fused deposition modeling, wire arc additive manufacturing, electron beam freeform fabrication. Okay. And whereas in case of powder based, the key techniques are selective laser sintering, electron beam melting, selective laser melting, and also laser metal deposition. So, so selective laser melting can also be called as LPBF, laser powder bed fusion. Okay. So, and then the liquid based techniques are stereolithography, it is mostly applicable to polymers. And your digital light processing, that is DLP, and then material jetting. So, these are the different additive manufacturing techniques. So, let us focus into the general principle. So, in powder bed fusion for metals, a laser selectively fuses a powder layer defined by the cross sectional area of a 3D model. Successive layers of powders are fused by the laser to form the final part. So, you can see this is a typical powder layer thickness shown over here. So, in reality, so the stage stage gets lowered and the successive powder layers are deposited. So, once the powder layer is deposited, then again the laser beam cures that powder layer, and thereby from the powder state of matter, the powder get fused, and the solidified part made out of this laser powder bed fusion technique can be obtained. Okay. So, later we will learn about how because of the laser energy laser based melting and solidification of the matter in case of LPBF, how the microstructure evolves because of that. We will learn subsequently in this module. So then so depth of laser penetration is typically greater than the layer thickness, allowing for solid layers or multi-layer fusion. Okay. So, what does it mean? So, you can understand it from here. So, you can see that although the deposited layer thickness, so because of the densification and because of the so that is why you can see the thickness of the powder bed which is deposited on top of the first layer. After solidification of that layer, the height slightly changes because of the porosity present in the powder particles that get densified when it is transformed into liquid, and then again re-solidified in the form of a solid layer. And the more importantly is that you can see over here that the laser beam is not only impacting the layer which is getting deposited, that is in this case say this is layer 2, this is layer 1. So, it is also penetrating up to a certain depth into layer 1. So, this is that means you can understand that the layer 1 is experiencing remelting up to a certain depth, and from those remelted region the solidification begins. We will learn about the microstructural changes this remelting causes into the AM processed parts in the subsequent slides. Okay. So, so the advantages of laser powder bed fusion, number 1 is high material density. So, LPBF processes produce metal components with near full density. So, this is very important to know, ensuring superior mechanical properties such as higher strength and durability. and number 2 is microstructural control. So, the rapid melting and solidification inherent to laser powder bed fusion create fine microstructures leading to enhanced mechanical properties, and then tailored microstructures can be achieved by adjusting process parameters like laser speed and power. And also there are other process parameters like laser spot size, and also there are morphology of the powders and powder morphology. Powder morphology includes powder shape, powder particle shape, and also its size. Okay. So, so the number 3 is reduced porosity and defects. So, advanced techniques and optimized process settings minimizes porosity, voids and other defects in the final product. And then here comes the number 4. So, number 4 is material variety. So, there are different kind of materials which can be processed by LPBF. Some of the prime application of LPBF is in the processing of nickel based superalloys, titanium alloys, and also cobalt chrome alloys. So, this versatility makes it suitable for critical applications such as aerospace, medical implants, and also automotive components. And number 5 is thermal management. So, precise control over heat input during the process helps to minimize residual stresses and thermal distortions. So, like we have discussed in detail about the residual stress and thermal distortion when we have discussed about the welding, and also we have when we have discussed the process modeling module of welding. So, those things are also observed in case of additive manufacturing, because you know that additive manufacturing, the idea came from basically from welding and also to some extent from powder metallurgy, or you can also say that in their combination is what the additive manufacturing today that we know. So, so then so there is a role of residual stress and thermal distortion in case of LPBF as well, because of the rapid solidification involved in this case, but precise control of the process parameters like heat input and also scan speed of the laser, it can be tailored or it can be minimized the residual stress and thermal distortions of the components after solidification, and also so this improves part integrity and dimensional accuracy. Okay. So, and then microstructural anisotropy. So, that is one of the key LPBF limitation. Why microstructural anisotropy? Because additive manufacturing can lead to anisotropic microstructures affecting mechanical properties like strength and ductility. So, what is the key reason of microstructural anisotropy? This is because you see that, as I already told, that the in case of LPBF, the powder build is getting cured or melted and re-solidified in layer by layer fashion. So, if I draw the typical microstructure which can be say columnar dendritic, again which depends on the the local thermal gradient and cooling rate, or if I say more specifically, then based on the G by R ratio, the microstructure depends. So, what is G here? G here is thermal gradient, and R is the solidification front growth speed. Okay. So, R is solidification front growth speed. Okay. So, so then based on that it depends that whether the in case of LPBF the microstructure will be whether it will be planar or whether it will be so if I write the transition that happens in case of typical in case of this in case of LPBF. So, then if I just a minute, okay. So, so this is the transition that happens with the, so I can say that G by R ratio with the decreasing G by R ratio, the transition that happens is of microstructure, that is initial. So, at high G by R ratio it is planar, and as G by R ratio decreases the microstructure becomes becomes cellular, and then if further decrease of G by R ratio happens, then it becomes cellular dendritic, and then it further decrease causes columnar crystals, or columnar primary phase, and then further decrease cause columnar dendritic, and then it is equiax dendritic. So, you can see that there are several different transitions that happens in case of additive manufacturing, laser powder bed fusion. It also happens in other kind of laser based additive manufacturing processes, that and also arc based processes. So, that we will discuss later. Let us focus our attention to LPBF now. So, then you can see that based on the local thermal gradient and cooling rate conditions and solidification front growth velocity, the microstructure changes. So, then you can see different microstructure in different layers, and also there is another aspect which demands attention, like the direction of the this heat flow direction. So, then that also, because we are talking about a elliptical melt pool like we discussed in the previous slide. So, you can see this is a elliptical melt pool. So, that is why the direction of this thermal gradient also changes, and then so then the evolving crystals or the dendrites, they try to follow the the direction of the thermal gradient, and then so but however that they these crystals grow along their preferential crystallographic growth direction. So, then so in the subsequent layer, the angle between the growth direction of the crystals and the the direction of thermal gradient or the heat flow direction. So, this angle theta is called the misorientation angle. Okay. So, as the misorientation angle decreases, the microstructure is going towards single crystal microstructure. So, that is also possible to be manufactured by additive manufacturing. So, but we will talk about that later. So, you can see that because of this physics based reasoning, the microstructural anisotropy has been evidenced in case of additive manufacturing. And then flaw content and discontinuities. So, defects such as microporosity, incomplete fusion and cracks are common in LPBF. So, these flaws adversely impact fatigue life, toughness and creep resistance of the LPBF processed parts. And then number 3 is the material specific challenges. Certain challenges such as titanium alloys require optimized conditions to prevent metastable microstructures that degrade performance. And then number 4 is residual stresses and distortions. So, rapid thermal cycles during the process introduces residual stresses leading to warpage or distortions in the final part, after solidification. And post processing dependence. So, heat treatment or hot isostatic pressing is often required to address microstructural and stress related limitations, increasing time and cost. So, these are the prime limitations of the LPBF. So, that for example, this heat treatment is very important in case of LPBF parts. They cannot be subjected to the service without heat treatment, because you see that because of rapid solidification involved, there can be microstructural anisotropy. There can also be anisotropy in terms of the precipitate size and shape and morphology and their distribution across different layers of the LPBF build. So, then to homogenize the LPBF process part, it is important to homogenize the part and also subsequent aging treatment. So, the heat treatment is essential for LPBF parts. So, that also increases the cost to some extent. So, the thing is that this LPBF based additive manufacturing can be implemented to some precision components, where you know that the cost is not the prime factor, rather the complicacy of the parts and also achieving them into that desired design, and also when it is when it is in small size it is needed. So, then when precision is on demand, and also for batch production of critical parts. So, when the moment you need to move to mass production, So then it is of no use to I mean go stick to AM, that then it can be moved to the conventional subtractive manufacturing techniques, where it can basically decrease the cost with the increase in number of parts. Okay. So, so now let us summarize the advantages and disadvantages of LPBF. So, these advantages are complex structures can be developed and rapid prototype time to market. That means there are many stages in other conventional manufacturing techniques what we have discussed in detail within the scope of this course. So, you can see that additive manufacturing in specifically LPBF, it can be done at a very directly, without going into much intermediate steps. So, directly from powder state you can get the 3D solidified object made. So, that also decreases the time lead time needed from concept to the market stage. So, so that is also a key advantage, and then other advantages are good accuracy. So, that is why complex structures can be promoted to be manufactured by a laser powder bed fusion, and another is multiple instances in one build cycle. So, these are the advantages, and what are the disadvantages? Disadvantages are particle size limits. So, LPBF demands for fine powder particles, and also it demands for spheroidal powder particles. So that also so spheroidal powder particles, so that also increases cost of the powder particles, because it can only take the powder particles which are manufactured by either gas atomization or centrifugal atomization, or even plasma atomization. So, that means you can understand the cost increases because of the specific size and shape requirement of powder particles, and then there is chances of porosity, void and defects that we discussed, slow deposition rate compared to other laser based processes like directed energy deposition, distortion and cracking. So, these are the disadvantages of LPBF. So, now we will move to directed energy deposition. So, what is direct energy deposition? So, in case of direct energy deposition, which is also known as LENS, laser engineered net shaping, or DMD, that means direct metal deposition, involves depositing metal filler into a 3D shape through a computer controlled nozzle and laser beam. So, the major thing in case of DED, the major difference with LPBF, as there is DED does not need any powder bed. Okay. So, that means you can see that already we have discussed that like for this additive manufacturing can significantly decrease the material wastage of what happens in case of subtractive manufacturing processes, because of the removal of the extra material or the allowances given, the material corresponding to those allowances during machining stages. So then LPBF, if you compare with subtractive manufacturing processes, it already saves material, and then DED saves further because it does not need any powder bed. So, it works based on the principle of a coaxial nozzle. So, then what does it do? So, then this annular space is filled with powder. So, the powder gets deposited on a substrate plate. So, likewise, like I am trying to draw here, and the laser beam impinges on on the deposited powder, and then it cures it. So, thereby you can get the 3D object made, or the powder build is possible to be made over the substrate plate. Okay. So, this is your substrate. So, then you can understand that it can significantly reduce the wastage, or because of non requirement of powder bed. So, this is your coaxial nozzle, nozzle. Yeah. So, then comparison with LPBF, DED produces fully dense metal deposits similar to laser powder bed fusion parts. Unlike LPBF, DED focuses on adding layers to existing components or create freeform 3D structures without requiring support material. So, then that is also another key difference with LPBF. So, as I told you in the previous slide that LPBF is useful for small size precision key parts, whereas DED can be effectively utilized for repair purposes. So, DED can be used for repair purposes, for example, this turbine blades. So, like for I mean high temperature jet engine aircraft engine turbine blades. So, there if there is any crater or I mean defect forms, so then those defects can be very well be nullified or cured by depositing the I mean same material out of which the turbine blade is made up by directed energy deposition route. So, I mean this can be effectively utilized for repair purposes, and application used for additive repairs, cladding and creating large scale components. So, the limitation in terms of part size that I have discussed in case of laser powder bed fusion is not there with DED. So, the DED can effectively provide larger components, okay. And also cladding, it can basically generate a surface layer. So, for example, there are some metals like aluminum and more importantly magnesium. So, they are very reactive and also prone to oxidation. So, laser cladding can be employed to deposit a layer of material which can protect these metals from the environmental hazards. So, that is also a key applicability of directed energy deposition, and it integrates laser cladding with 5-axis CNC control for flexibility in handling complex geometries. And then advantages and challenges. So, advantages are rapid material addition, no need for powder bed preparation as I discussed before, suitable for large scale application, and challenges are complexity in software and hardware integration, requires precise parameter control, that is focal spot size, beam positioning, etc. Okay. So, I mean yeah, so this is a typical schematic of the I mean directed energy deposition process. So, what you can see, there is a laser beam which is focusing through this coaxial nozzle, and then this is the powder delivery nozzle. So, it is basically the part is getting built over here over a build plate or a substrate plate, and then so the material deposition, liquid phase sintering ensures full material densification, microstructure evolves due to rapid cooling and solidification during deposition, and then thermal effects. So, high thermal gradients result in refined microstructure, but may induce residual stresses. Subsequent layers help alleviate thermal stresses, enhancing structural integrity. Okay. And then number 3 is material versatility. So, suitable for various metals and alloys including high performance materials like titanium and nickel based superalloys. Okay. And also like in situ alloying is possible I mean in case of DED in a much more effective manner that than we can get in case of LPBF. So, you can basically, so you can see, so these hoppers you can use 3 different powders, say A, B, C. So, then you can basically I mean deposit them sequentially to facilitate in situ alloying and also to I mean to generate functionally graded parts. So, in situ alloying and developing FGMs. So, functionally graded parts. So, these are the potential I mean advantages that can be offered by directed energy deposition technique. And then number 4 is microstructural refinement. So, fine grained microstructure and minimum porosity are achievable due to controlled energy input, and post deposition treatments, that is heat treatment, are often necessary to relieve stresses and optimize mechanical properties. So, with this we are stopping for this class, and we will go into the further detail of additive manufacturing processes, and we will see how we can apply process modeling to I mean grab insight into the additive manufacturing processes in the next class. Thank you.